Okay, so I guess we can start now. My name is Audrius Jasaitis. I will be the host of this webinar today. And so hello and welcome everybody to our webinar on adaptive optics. This is already the second such online event in a series of dedicated webinars to microscopy. And today's webinar is called Adaptive Optics in SMLM for Deep Tissue Imaging. And it will be presented by our remote guest from Utrecht University, Marijn Siemons, who works in the group of Lucas Capitaine. He kindly agreed to present their latest developments from their lab in the field of adaptive optics and aberration detection for super resolution microscopy. This is a brief outline of today's webinar. So I will do a quick introduction to Imagine Optic. Then there will be a presentation by Marijn and also hands-on part made by Marijn. And there will be a question and answer session. Most likely we will do one more session between the presentation and the hands-on. So please put your questions into the chat. This you can find on the lower panel of your interface. Please send the questions directly to organizers, and we will try to answer these questions in 2 sessions. So I will start by introducing a couple of words Imagine Optic. Basically, Imagine Optic is a French company which is specializing in adaptive optics and waveform sensing. It has been founded in 1996 and already for almost 25 years is offering its expertise in the following fields, as you can see on the screen. Since beginning, Imagine Optic is specializing in Sharp-Hartman technology of the waveform sensing, and currently we are offering to the market the whole range of very high accuracy waveform sensors in various spectral ranges, which are all, and the major feature of these waveform sensors that they all can measure with lambda by 100 precision RMS the wavefront. A second big group of our products is the adaptive optics and deformable mirrors, where we also have various designs starting from small and fast deformable mirrors, which are using electromagnetic technology and used in microscopy, as well as larger size, very large size deformable mirrors with mechanical actuators, which are used to steer and optimize the beam of high power lasers. And of course, the third part, which is linking the two components, is adaptive optics software, where we put all our knowledge gathered during this all 25 years of experience of basically to fine-tune and to give the best result in the so-called closed loop, open loop measurements, and basically the advantage of very precise wavefront measuring gives you the opportunity to obtain very good result in the wavefront correction. We also supply different kinds of systems and also larger systems, and we provide engineering services for specific needs. For microscopy, we are offering separate components of adaptive optics. So these would be deformable mirror, so MicAO 52E, 52 actuator deformable mirror, together with the wavefront sensor and the software. We call this package EO Kit BO. It's designed for implementation in the custom build setups and can be used in wide field microscopy, super resolution, 2-photon microscopy, scanning, or number of scanning techniques, light sheet microscopy. But this set of components the implementation would be designed by the customer. For easy implementation on standard microscopes, we also provide this device called MicAO 3D-SR, which also contains deformable mirror inside, and it can be easy attached to the standard microscope frame, and would give you quick correction of the wavefronts. And this is what Marijn will be presenting mostly today. So I will now give the presentation rights to Marijn, and I think he will continue the presentation. Just a moment. Here we go, Marijn. Can you? Yes. You are muted. So could you unmute your your microphone? Can you try to unmute your microphone?
Yes, it works. Okay. Yes. Hi, everybody. Thank you for the kind introduction, Audrius. I'm very excited to share one of our latest works here on the depth optics for single molecule localization microscopy. So today I'll give a short presentation outlined here with a small introduction. I'll talk about the setup and the calibrations and some tips and tricks to get the system working correctly. And then I'll talk about the issues when you start to image deeper into complex tissues when you want to do 3D single molecule localization microscopy. And then in the third part, I'll talk about how to do depth optics based on the blinking molecules itself, so no fiducial marker. And I'll give a short demo as well for this. Yeah, so I would say let's get started. So just a quick introduction to single molecule localization microscopy. As you all know, standard microscopy is limited by diffraction, and SMLM overcomes this by a simple trick, basically by inducing sparsity. So normally all the PSS would overlap fluorophores, by just sparsely activating them, you can localize them with precision, typically of about 5 to 20 nanometers. And then if you take a video of a stream of acquisitions, you can all localize these individual blinking events, and then you can reconstruct the so-called super resolution image, which typically has a resolution of about 50 or 80 nanometers. Yeah, you usually take about 5,000 or 40,000 frames, and you have maybe up to 1 million or even more events depending on your field of view size. So this is quite a strong technique, and it's mostly used on cells plated on a cover slip. So if you want to image deeper into your tissue or sample, the wavefront will get aberrated, it gets distorted because the light is retarded differently due to the structure of the tissue. And now the point spread function spreads and becomes much harder to detect and localize these blinking events. So depth optics is a way to overcome this by correcting these aberrations. So the central question basically of a depth optics is how to find the correcting shape of the deformable mirror. So traditionally, you can use a fiducial marker and optimize the intensity of the fiducial marker, or use a wavefront sensor in combination with this. A very popular way of doing this is just optimize the image itself and find a proper metric to optimize. So for instance, contrast of an image. This is generally very hard for single molecule localization microscopy because of the blinking. Each frame will be different, will have a different amount of emitters, different focal planes, and a lot of noise. So I'll talk about this, our way of where we find, or we think we have a robust way to correct for these aberrations. Before I get into that, I want to talk about setup and basically part 1 and 2. So let's get started. So this is the setup we have. It's right here behind me. You can see the MicAO box as well. And on the other side, we have a cylindrical lens module from Nikon. So we can actually do both types of astigmatic Z encoding in this setup. So as you can see here, we have the Depth optics module, and then the Siemons camera. On the other side, we have the cylindrical lens module. So the way we calibrate the setup is we use the Shack-Hartman sensor, the HASO. And the Shack-Hartman sensor just very quickly uses a microlens array, and then the displacement of the focal points is basically a measure for the local slope of the wavefront. So what you can do is you can make a sample with beads and then measure this the pupil. So here already is quite an interesting thing. If you just use beads and water and you have an oil immersion objective, then there's quite a lot of apodization in the pupil. So I just plotted it here. There's quite a strong intensity difference over the pupil itself if you use, for instance, air or water. And you can see that here. So this is a measurement from the HASO. And you can see that in the center, there's a lot of lower intensity. And it actually becomes much better if you use an oil as a mounting medium. However, oil is not a stable mounting medium because the fluorophores will diffuse to the oil. So I found the best way of doing this is to actually use glycerol. It's a high refractive index and very close to oil, and the beads are very stable here. So my first step would be, if you calibrate, use glycerol as a mounting medium. Another thing, which is also quite important, is when you calibrate, you have this option to exclude sub-apertures. So basically exclude a ring from these dots here. So if you want to accurately calibrate your deformable mirror, it's very important to set this to 0. It will be more robust if you exclude sub-apertures, but for an accurate calibration, you really need to set this to 0. Yeah, so that's trick number 1. And then the way we verified this calibration is using phase retrieval. So my startup routine, usually I turn on the device, wait a couple of minutes, sometimes even an hour, to get it thermally stable. Then I place a bead sample and I take it through focus scan, as you can see on the left. And as you can see, it's not perfect. And it has to do with some drift in the mirror. Because every time you start up, there's a different temperature, and that will flex the mirror slightly. So I then take it through focus scan and then perform a phase retrieval algorithm, which estimates the Zernike modes, here the blue line. And I then send the correcting command to the deformable mirror and perform a through focus scan again, as well as the phase retrieval. As you can see, most of the modes are actually corrected now. There are still some higher modes visible here. So these are in the 6.2, 6.4. And we found that the mirror has 52 actuators. So it cannot accurately modulate these higher order Zernike modes. So this is kind of the base level of correction you can achieve. So after I've performed this, I place my real sample that I want to image, and I can do my aberration correction. Another way to verify your calibration is to then modulate specific Zernike modes and see if you can find these specific Zernike modes in your phase retrieval. So this actually works very well for Zernike modes up to the 4th order. So as you can see here, we nicely pick up all these modes. However, for higher modes, so this is 5.1, so 2nd order coma, for instance, you can see that we get crosstalk between these Zernike modes. So the mirror, only with 52 actuators, cannot modulate these higher order fields. And it's also important if you don't, or if you crop your pupil with excluding the subapertures, this accuracy decreases. So it's very important to fill the DDM completely with your beta if you want to do accurate wavefront modulation. Okay, so as most of you probably already know, a very popular way of doing 3D single molecule localization microscopy is astigmatism based. So you can either use the cylindrical lens or use a deformable mirror to introduce astigmatism in your phase profile. What now happens is that your point cloud function will elongate in a certain direction, depending on the position relative to the focal plane. If you now plot the width in the x direction minus the width in the y direction, you get kind of these calibration curves. So based on this, you can estimate what the Z position is of the fluorophore. So we wondered which of these methods is actually preferable. How do they perform? So first, I looked at the field dependency of these both modules. So with the cylindrical lens, I measured the total level of aberration across the field of view. So here I just noted it's just kind of the center of the CMOS chip. And this actually matches reasonably well. So the red line indicates the diffraction limit. And this resembles basically the performance of the MicAO module as well. Interestingly, the most dominant aberration profile of aberration in the field is in the case of the cylindrical lens module, astigmatism. You can see this very cool kind of dipole structure, these nodes. Whereas for the AO module, coma is the most dominant aberration. If you now introduce astigmatism, or by putting the cylindrical lens in, or by modulating astigmatism by the deformable mirror, we can see that the amount of astigmatism varies quite a bit with the cylindrical lens across the field of view. Not only the amount, but also the angle changes. Whereas this is much more homogeneous when you use the depth optics module or the MicAO. Secondly, there's also a slight demagnification when you use the cylindrical lens, which is not present when you use the MicAO box. So this is not a really big problem. Actually, both of these effects are, you can correct for them computationally, but you have to take that into account. Okay, so let's get on to part 2. So what happens when you start to image deeper into your sample? Can we still do astigmatic Z encoding? And the answer is actually no, or not without the depth optics. If you use the cylindrical lens, you start to image deeper into your sample. This is an oil objective and a water, basically an agarose gel with beads. You can see that the ellipticity of the PSF gets diminished and is almost completely gone at the depth of about 15 microns. Now with adaptive optics, we can correct for the spherical aberration and then introduce even more astigmatism to maintain a calibration curve very similar to the calibration curve close at the cover slip. So interestingly, if you use a water objective and a cylindrical lens, you also maintain the same calibration curve. So this already indicates that the spherical aberration introduced by the mismatch of the refractive index of your immersion as well as your sample are the main root cause for this loss of ellipticity. To investigate it further, or at least try to see if we indeed are correct, I performed some modeling of this. So these two plots indicates the phase of the pupil at a depth at the cover slip or about 50 microns into the sample. As you can see, at the cover slip, we have a very nice point spread function where the ellipticity is clearly visible, and it's no longer the case when we image at 50 micron depth. The way as shown here, actually I cropped, I stretched the contrast between 0 and 1 lambda. Actually, when you don't or fully stretch the pupil, you can see that at the edge of the pupil, there's this huge retardation of the wave, almost up to 10 wavelengths. And the astigmatism is basically drowned by the overwhelming spherical aberration. Also, when we compare the point spread function, what we measure with our simulations, we can actually see a very clear match between the two, indicating that our model captures most of the effects that we see here. Okay, can we indeed get the same calibration curve if we use depth optics? So if we do this, correct for astigmatism, and only add 60 nanometers of astigmatism, we get some ellipticity in the PSF, but it's not fully back. And indeed, we seem to need to add more astigmatism to get the same ellipticity as at the cover slip. We also compare this for different depths. We see that we get a reasonable, or that reasonably compare well with the experimental values. But again, in the experimental values, there's also quite a large deviation in the precise calibration curve. Okay, and also what's quite interesting actually, that the precise calibration NA has quite a large influence on the astigmatism which is needed. And in this case, the NA of 1.43 matches with a single subaperture which is removed from the calibration. So this slide shows that we can use this to perform 3D single molecule localization microscopy with oil. Here in the case of a depth of about 12 microns. And here we image microvilli, so of Kaku cells. These are epithelial cells, and they make this kind of finger-like structures, which they use to absorb nutrients. And interestingly, there are quite a few people who have defects in this. It's called microvilli inclusion disease, and they don't properly make these microvilli, which cause all kinds of problems for the nutrient intake. So we image these microvilli with storm, and we used a bead as a fiducial marker to perform a depth optics and just optimize the intensity of the bead. So after this, you can see that we can really resolve these microvilli. In this case, in panel C, you can see 3 microvilli laying on top of each other, which we can resolve in the C-axis. Okay, so this is pretty cool, but you still need a bead to do this. So ideally, we want to use the single molecule acquisitions themselves because it's very hard in a lot of samples to precisely put a fiducial marker somewhere where you want to image. So this brings me to part 3. So as I mentioned earlier, the sample-induced aberrations hamper detection and localization of these events. And that depth optics can correct for these, but as placing a fiducial marker is difficult, so we want to use the intensity of your frames. So to use this, you basically need 2 things. You need some kind of quality measure of your image, which is called a metric, to optimize, and you need an optimization scheme or algorithm to do the optimization. So previously, there have been 3 main methods to do this, that have been proposed to do this. As a metric, they all propose to use the spatial frequency content of your acquisition. So you take an acquisition and then take the Fourier transform of that and look at the spatial frequency content of that acquisition and basically try to optimize this. So here you can see the 3 different metrics, kind of with a cartoonish way of describing it. As an optimization scheme, they all propose different methods. So Burke et al. Uses model-based optimization, Tirani et al. Particle swarm, and Nosotski et al. Nelder-Mead simplex. So I won't go into a lot of detail about this, but very short, model-based optimization uses some kind of model or prior knowledge on that you know how a certain Zernica mode would affect your metric. And that's called a model, and you can use this information to estimate your correction. Particle swarm has kind of a lot of solutions floating through solution space, and they influence each other like a swarm and try to find the optimum. And Nelder-Mead simplex uses some kind of triangulation in each parameter direction to find the next step, and then iteratively converge to the optimum. So interestingly, there's not a lot of known how do these methods actually perform. They show some improvement in their publications, but a true comparison between these 3 has never been performed. So we set out to do this. And I used a DNA paint sample where imager strand binds transiently to the cover slip, basically mimicking linking. And the advantage of this is it's a very stable sample. So we can have the same image or let's say signal and background levels for every experiment. So here you can see 2 different or non-aberrated and aberrated PSF. And what we could do is we can induce a known aberration. Because we calibrated our deformable mirror with such a precision, we know that we can accurately modulate all these aberrations. We then perform each Depth-Optic method and evaluate how they corrected this. So if we do this, let me just show you or introduce the graph. So we introduce an aberration level of about 3/4 of a radian, this line here, and then use the 3 methods here described earlier. So this would be Burke et al., this Tirani et al., this Nosotski. And then interestingly, none of these methods actually achieve proper correction. So that would be this gray region where the serial ratio is higher than 0.9. So we have investigated why this actually was the case. So if we look at the Fourier spectrum of these images, we can see that most of the difference lies in the low spatial frequency content between 0 and 1. And then if we look at these metric values or the metric weights, we can actually see that the metric of proposed by Nosotski et al. Only measures the low spatial frequency content. This is where actually the largest change is. Nothing really happens after 1 NA over lambda. So if you're looking at this and try to optimize this, you're just looking at noise, which makes it harder to correct. However, their method also didn't perform well. So the question is, why did that happen? Well, these metric values are still very noisy. So your correction algorithm also needs to have some kind of way to reduce the noise even more. And that's model-based. With model-based, you can use prior knowledge of how your specific Zernica affects your metric, and you can use this information to lower your noise. So we thought that combining metric 3 with model-based optimization will result in a more robust and reliable correction scheme. So fairly quickly, model-based optimization, you take a sequence of biases which you apply for a certain Zernica mode, and then you calculate the metric value, and then you fit a curve through this. So it's called the metric curve. Then you find the optimum, and then you go on to the next Zernica mode. So this is sometimes called 3N correction scheme, but it depends on how much biases you take. So we did a lot of optimization for this, and we actually found that we need to take about 9 up to 13 biases per sonic mode to get reliable correction. So it's a 9 or a 13N correction. Secondly, Gaussian with an offset corresponds quite well with the metric curve. And we found that we need to repeat the correction scheme multiple times to improve the correction. So here again, I've shown you this graph partially before, but now we added our method, which would be the right part of this. You can see if we do this multiple times, we can get a very robust correction with a stereo ratio above 0.9. So our method takes about 300 acquisitions and can correct aberrations up to 1 radian in a realistic signal and background ratio. So here you can see a plot where we increase the aberration level and then see how well our Depth Optic scheme was able to correct that. And you can see that 1 range is just about what it can do. Afterwards, it just gets too big to properly converge to a maximum. I want to stress also that we actively tuned the signal and background levels to realistic values, which we found when we imaged into slices, grain slices in this case, which is about 10 to 20 meters per frame. And they, on average, emit about 200 and 500 photons with background levels between 10 or 40 photons per pixel. Okay, so time to test this in our real sample, a partially real sample. We use a sandwich assay. So basically, we're imaging cells through a brain slice. So basically, we put a cover glass coated with cells or stained cells, and then a brain slice in between, and we image through the brain slice. And then performed something called localization microscopy. But first we did our Depth Optic scheme, and then we switched during the acquisition between a corrected and a non-corrected state. So as you can see, this makes a huge difference. We can see up to a 6-fold improvement in the number of detected events, which makes it much easier to get nice reconstructions. Okay, so we adopted our method and called it REALM, which stands for Robust and Effective Depth Optics in Localization Microscopy. And because we thought this is a very valuable addition to the microscope field, we made an open source micromanager plugin. So you can find it here, and this is what I'll be demoing today. It uses the MicAO device adapter, which I wrote as well. If you're not a fan of it, there's also a device adapter for the Torlabs mirror as well. Okay, then lastly, a real sample. In this case, we stained for spectrin and red brain slices and imaged these at the depth of up to 50 microns. And spectrin is a associated protein with the actin skeleton, actin side skeleton, and has this very periodic spacing of about 190 nanometers, which is found in neurons basically image on a cover slip. So we also performed this, as you can see, we can very nicely resolve the spectrin structure. We get a very good 3D circular, or elliptical in this case, reconstruction. So REALM allows us to really translate from cellular or cover slip based cellular proteins to structures inside tissue. Lastly, in Outlook, so why would this be beneficial? So one of the things is that electrophysiology is performed at a depth beyond 30 micron deep. If you cut it, you want to have brain cells neurons which are healthy and which are not damaged when you cut the brain. So these are performed beyond 30 micron depth, and now we can actually combine the information of electrophysiology with the nanoscale structure we can resolve using single molecule localization. Okay, this looks all very exciting. So this is kind of a, how to call it in English, a way of neutralizing it a little bit. Deformable mirrors are not perfect. They introduce a base level of aberration. There are some transmission loss. They're also not cheap. They're often also not very plug and play. And our hope is that Realm will make this a lot easier to make it more plug and play. Just correct for a beat and then start imaging. Also, it's very often that the spherical aberration is the most dominant aberration, which is caused by the mismatch between your immersion and your sample. So you can try different objectives, maybe glycerol or silicon, and if that works better, that might be a good option. You can also change the correction color and ensure proper mounting. So use spacers, for instance, to ensure that the cover slip is flat with regard to your objective. And then other Zernike modes, apart from spherical aberration, mostly become apparent beyond 30 microns. So if you're below than that, you might not need depth optics, or the improvement caused by depth optics is not that big. However, if you want to do 3D localization microscopy, then you really need the depth optics to ensure that the calibration curve maintains the same value, or maintains the same. Okay, so this brings me to the end of the presentation. For some reason, yeah, here we are. I'd like to thank Lucas Kapitein, my supervisor, who has been great for the past 3 years, and all the members in our lab. I want to thank Naomi Hademeyer from the Neurophotonics Consortium, where we image the spectrum, and Audrius for a lot of help and debugging and to get me going with the system. Okay, now it's time for the demo, but maybe we can do a few questions.
Yep. So thank you very much. Thank you very much, Marijn, for your presentation. It was very, very nice. I also am very optimistic for your method in terms of simplifying the aberration detection routine. And on everyday basis, this should be very, very easy then. We have one question for you. So you are using astigmatism for 3D. Could you, can you tell us why did you choose that? There are other ways how to do 3D, like tetrapod, for example. Can you do this with the deformable mirror?
Yes, you can indeed do more fancy PSAF engineering with the deformable mirror. However, for these kind of Z encoding, you need quite a lot of very high intensity values, and this becomes just more difficult for slices to get really good signal levels. So I would say, or maybe hope, that would be indeed the next step, to maybe use a tetrapod PSF. But at the moment, the background levels are the most dominant, or they kind of are the limiting factor for how deep you can go and how well you can image. And if your signal value is just not high enough, then you cannot do tetrapod imaging as well. So we're also working on novel staining techniques to reduce the background significantly, and then that actually might work.
The advantage of tetrapod would be that you can get larger Z range at once.
Yeah, indeed. So currently we do multiplane 3D imaging. So we take multiple planes and then stitch them together to create a full 3D image.
Of thicker sample, yes, I see.
Yeah.
Right, thank you. One more question is, so you have to calibrate the system with the Hartman wavefront sensor. How frequently do you have to do this?
I think I did it twice. So I would say once a year, probably good. In principle, when you calibrate it and you don't touch it anymore, you don't need to do it. But yeah, once a year is probably a good idea. Just to
basically, if you change something in the optical setup, then you would have
indeed. Or if you change objective. So we also have a silicon objective. This of course needs a different calibration. Yeah.
Okay, thank you. There are no more questions for the moment, so we can probably proceed for the hands-on part.
Yeah, okay, cool. Exciting. Okay, can you guys see my micromanager screen?
Yes, perfectly. It says Realm, micromanager and Realm,
yeah.
Yes.
Yeah, okay, cool. Yeah, so this is the plugin. Let me just quickly go through it. So you have some settings tab where you can say the NA and the wavelength. Then you can choose here the Zernica modes that you want to correct. And here are the number of correction rounds which you want, the number of biases, and the bias range. So these are the three dominant aspects of the correction scheme. And then you can also choose here to show the specific metric values and fits. So we're going to tick this box and then choose your device. In this case, it's the BRA 52. And then we can go to the aberration correction tab. It has a very nice start button to kind of make it user-friendly. And then it mostly has three important buttons. One is the save wavefront, so you can save a specific state and you can load the specific state of your behavior and then save your correction data. So we can now go live imaging. So currently I have a sample mounted in the microscope with beads and Alexa Sigma 7 coded to the cover slip. So it's not very interesting for a reconstruction, but it's probably such a very nice demonstration of the use of Realm. So as you can see here, this is our bead, and I can go through focus. So it looks reasonable, but not perfect. So this might be, for instance, some drift in the system. So we can start off by just using Realm to correct or flatten the deformable mirror. Let me just, so in this case, maybe I can use 7 biases in just one correction round. And then start. So here you can see that it starts introducing a lot of aberration and then the specific fits of each metric curve. So the better this resembles the curve, the more precisely you can estimate the center of or the correction value. So it also spits out the estimated Zernica coefficients, the estimated wavefront profile. Let me just remove this. And also the Fourier transform of the acquisitions, which was based, where the metric values are based on. So you can kind of go through this as well. And basically, this will be the magnitude transfer function. And because we have such a high signal value, we see basically the whole cone of the MTF. Okay, so now let's see. It actually got a bit better. This looks pretty good. So this would be kind of representative for the PSF, what you can have with such a system. Now let's go for some single molecules. Let's find a place which looks really good. Yeah, so now we have some blinking. However, this is quite a lot, and we also have very little background. So to make it a little bit more difficult, I'm going to open the bright field shutter. So that's over here. I hope you guys could see that. So it actually introduces a bit of background. If we look at our average value, or I know by heart that this kind of resembles 50 background photons per pixel. So again, if I close it again, you will see that it will drop about 100, and we have a conversion factor of 2. So let me do this again. Okay. Now we are going to introduce a specific aberration. But first, before we do that, let me save this wavefront and then load it again. So in this case, the mirror thinks it's flat, and we can add a little bit, let's say, of astigmatism and maybe some coma as well. So let's do some coma and maybe some spherical aberration as well. Now I can just stick this, and then I've introduced the aberration. So now the contrast definitely reduced. We can also switch back to our bead and to inspect our PSF. So this is a bead, and as you can see, there's quite a lot of aberration in this case. So it's definitely no longer a very nice PSF. Okay, let's get this out of here. So now let's try and see if we can correct the aberration based on the blinking of the molecules. Let me get them in focus. Maybe we can wait a little bit to reduce the signal levels. Okay, I'm going to save this wavefront. It's aberrated. And then load it again. And now when we look at the vertical modes, the mirror thinks that it's flat. Okay, so let's correct, in this case, the low. This is astigmatism, coma, and spherical aberration. Let's take 2 correction rounds with 13 biases. And then let's just start. So here again, you can see the specific metric values and the fit of the curve. And because we have such a high signal level, we have a very good match with our fitting, and we're able to estimate these coefficients with a very high precision. In a real sample, this would be more difficult because the signal level is lower and the metric values are just much more noisier. So this is round 2, and again, you hope to see that it's like this, very symmetrical on each side, and then you know that you corrected each mode with a high precision. So again, we have the estimated wavefront. You can give it a nice color like this, and the Zernicke coefficients. So if you remembered well, we had 0.2 of astigmatism, 0.3 of coma, 0 coma in this case, and we had, I believe, 0.3 of spherical aberration as well. So here this seems to be quite a bit of a mismatch there. So now we can look at the punchboard function as well and see how well it corrected it. Again, here's the Fourier transforms, and you can see very nicely that it tries to optimize spatial frequency content. Let's switch to beat. let me close the shutter as well. So this PSF, as you can see, it's much better. There might be a little bit of coma left, but it's hard to say. Yeah, so this, in the case of when you want to estimate these aberrations, you will make a small small error every time. So as you can see or saw on my presentation, it's not perfect, and there is some offset because when you correct each mode, there's a slight error as well. So, but you can definitely do much better imaging with this point-mode function than the previous one. Okay, that concludes the demo. Are there more questions?
Okay, well, this indeed shows very nicely that the method works. I didn't see any comma left.
Yeah, maybe I'm very strict.
Yeah, we have, well, there's one question which you partially started to answer about the signal to noise level. What are the limitations here? I guess if you have a highly labeled sample, with a high density labeled sample, and try to go deeper inside, your signal to noise level would decrease quite significantly very quickly. What would be the limitation? How deep can you go with this?
Yeah, that's a very good question. So I think the background is the limiting factor. If you have 100 background photons, you might still be able to do it. But if you have maybe 500 background photons, that it just becomes impossible. So the real situation is probably has a large influence on the background. If you want to look at microtubules in slices, then basically everything will light up as a Christmas tree. But when you use D-storm, direct storm. However, there are also other ways of doing single molecule localization microscopy, such as PALM, or you can maybe use a light sheet excitation, or novel staining strategies. So if you use, we are working on a system, or a group that we work with is working on a system where only a couple of cells inside the slice will have a knock-in of a specific protein, and we can label this knock-in with the halo tag, for instance, and then only that cell will be labeled. So there's basically it's like light sheet microscopy, where you only have one cell that you're imaging.
Yeah, but this is also a very high level, I guess, molecular biology here. to have such a sample.
Let's see, I think I lost my sound.
We can hear you very well. Can you hear me?
I cannot hear you.
Oh. Can you hear me now?
Yes, I can hear you. Sorry. Okay. I think my cable just got unplugged.
Right. Okay. Yeah, well, that kind of sample would definitely solve the problem, but it's quite high-end, let's say, high-end sample.
Yeah, indeed. So I would say test it, try it. I cannot answer it for the specific structure that people are interested in. Yeah, it depends a lot on your staining, your specificity of your antibody, and things like that.
Yeah, I see.
Yeah.
Okay. One more question is about how many biases. So like if you would use a merit factor of maximum intensity, typical value is 3. So three images would be enough to detect the maximum quite well.
Yeah.
What's the minimum number in your case for your merit factor?
In the case of the 3N algorithm for maximizing intensity, you can basically assume that the noise is negligible. So then you can look very close to the optimum and take 3 points around this and use a parabolic fit to find the optimum. In this case, the metric value is much more noisier. So let me see if I can share my screen. Let me go to slide. I can see over here that when you take a number of biases, there's quite a bit of fluctuations in this. And then if you only look at close to the optimum, the noise is basically dominating. Whereas if you take larger biases, the value reduces significantly and becomes more or easier to estimate the correction or the correct value. I can also show you some optimization, which we did, where we changed the bias range. So here you can see, I think in panel C, probably the best. If you use a bias range of 1 radian, you get the best correction. And if you use only very small bias, then it's very difficult to achieve correction.
So indeed, it's very, very important. Yes. Okay. And then the number of iterations. It looks like you solved the problem in 1 run, but it's still iterative algorithm. If you have less biases, you probably would have to do more iterations then.
Yeah, so that's why they're kind of 2 optimums. Also, it's important to understand that when you the contrast in the metric value, so like the highest value and the lowest value, that depends on how close you are to the optimum with other zodiacal modes. So if you have, let's say, you want to correct astigmatism, but you have a lot of coma, then when you change the astigmatism, your metric value will go slightly up and then will go down, with a very small difference. But if you are very close to already corrected coma, you will have a large difference. So depending on what you know of your aberrations, it might be beneficial to first correct the aberrations which you know are there, first correct them and then move on to other zodiacal modes. In these simulations, we just put a random configuration, like it can be anything. Second order astigmatism, combinations with all of that. So if your first correction round, let's say you have your last correction is second order astigmatism, which is the most dominant one, then it's very hard to correct the modes of these ones that you're correcting first, and then finally you come to second order astigmatism, you correct that, and then you can actually do the correction values of the other modes. So the specific order also kind of influences the best strategy to correct. If you don't know which aberration is the most dominant, then it's more beneficial to multiple rounds, maybe with less biases. If you already know your most dominant aberrations, maybe go to less rounds and first do the most dominant ones, and then take a lot of biases, or increase the number of biases to increase the precision of your correction.
Okay, yeah, well, thank you very much. I think that covers most of the questions. Well, thank you very much. I think we can conclude on this point here at this step.
Yeah, perfect.
Thank you very much for your nice presentation, and thank you very much for all the attendees. We hope to see you in our next webinars, which we are going to organize in the nearest future. Thank you very much.
Thank you.
Bye.